Hi, Tomosha, Nicolás.
Cecilia, ahí tomo ya.
Okay. Wait. It's better. Okay, this should be better. Okay. Okay, can you hear me?
Yes.
Okay.
Yes.
Okay, thanks. So it's about time, so I'm gonna start as usual. So this week, we're going to do the midterm review again. And topics we're gonna cover are hypothesis testing again, with a little bit more, so to say, like conceptual, like with like higher overview of this concept. That's the first thing we're gonna do today. And then we're moving on to likelihood ratio test, which we didn't have time to cover a lot in the testing week. So that's the two big topics that we're going to cover. And if the time allows, I want to talk about Bayesian statistics, which is a third exercise in the recitation note. And that's also something we haven't covered a lot, not necessarily covered a lot, because there's so many things to cover for Bayesian statistics week. And yeah, so that's our plan for today. So actually, let's see. I will import the recitation. First thing is, by the way, can you see my screen? Do you see my screen? Okay. Okay, so
Yes.
Yes.
okay. Thanks.
Yes, we can see the recitation.
Okay, so this is the first question, first exercise will be something that I will cover, the first topic we're going to cover today. And let's see. So actually, there's not something new here. Everything, like every component you need to solve this question is already covered in the either in the lecture or in my recitation. So yeah, so it'd be great if you can start this question. But let's just go over the question together, and I'll give you some time to solve it. So as I mentioned, this question is going to talk about T principle of statistical testing. So it's going to be very conceptual question. So you're not going to see actual numbers, but like this is a question to test whether you actually understand what's going on and when you do hypothesis testing. And the goal here is to construct the test statistics and kind of like create so basically create a test statistics from the quantile of the distribution, of a distribution. So your goal here is that again, you design a hypothesis test with a specific level of simple null hypothesis. So we're not asking you to construct like the complex hypothesis, and just asking you to do a simple one. So as usual, the setup is very like simple. So we have an IID observation drawn from symplectically statistical model P. And the statistical model P has a true parameter theta, which lives in the parameter space big theta. And for any theta in the parameter space big theta, like this test statistics. So this is test statistics. So this test statistics follows some known distribution whose quantile is Q alpha. So do you have any idea what's gonna be like example distribution for Q? It's gonna be something that we learned in the class, but like, do you have any idea what kind of distribution is gonna generate test statistics we're interested in? So it's going to be something like chi-square, for example, distribution with some degree of freedom k. So this is, we use this distribution when we're doing the Wallace test, right? And if you're doing the likelihood ratio test, we're gonna see this distribution again. And also, if you're interested in asymptotic test, right? If you're doing asymptotic, like for example, z-test, we're using standard normal distribution. So these are this distribution corresponds to Q, and which we're gonna use to construct any test statistics. So that's like a basic setup. And do you have any questions so far? Are we all good about this?
Tomoya, you said that these are the two possible distributions because we are going to manage with quantiles. That's correct?
Yeah. And like, so that's one, that's a one good understanding. But like, as we derived in the lectures or in the recitations, we know that certain test statistics T corresponds to particular distributions. And you're right that because we know this how these distributions are basically how the shape of these, we know the shape of these distributions, chi-square distributions, or normal with 0 and 1. We can easily construct the quantile of these distribution once we get the test statistics. So I think your question is like on the spot. So we're kind of artificially choose this distribution, but like we also somehow know that we can derive test statistics that corresponds to these distributions. Does it answer your question or?
Yes, thanks.
Yeah. So, it's kind of both coincidence and like convenience, right? So we kind of tweak distributions to construct the test statistics that is nicely behaves, and that is very simple to construct simple to compute the quantiles. But that's not necessarily just coincidence, because we choose because there are some properties in the test statistics that like kind of not automatically, but like that leads you to construct these test statistics and these distributions to construct the quantile. So that's a very good point. But like, it's good to keep that in your mind. Okay, anyway, so let's continue. So we consider, again, we're having, again, the setup is we have n observations drawn from some statistical model. And we pretend that we do not know this true parameter theta. And we say, okay, we want to know, oh, wait a minute, sorry, this is a typo here. This should be theta star, actually, sorry. So theta star equals theta naught, or theta star is not equal to theta naught. So that's kind of that's a like test we're trying to do. So we have two questions here. One is to construct a test with a level alpha for the hypothesis above. and your answer should be in terms of Q alpha and Tn for some value of zeta naught. So this is very abstract question, but like if you kind of refresh your mind and rethink about how to construct the statistics, I'm pretty sure you can do this. And the second question is going to be, give a specific example that comes from this particular setup. It's not particular, but this very general abstract setup. So give me like a particular example where you can apply this framework and construct the statistics. Okay, so do you have any questions? If not, I'll give you, sorry, go ahead.
No, it's okay, it's okay.
Okay. So I'll give you like, say 15 minutes, 15 to 20 minutes to solve these two questions. Okay, so please take some time to look at these questions, and yeah, I might go to bathroom now, but like I'll be back soon. So if you have any questions, just feel free to chime in or just leave something on your comments. Okay.
Okay.
Feel free to talk and discuss, okay, as well.
Hola, Igor.
Hola, Rodrigo. Bien, ¿y vos?
Bien, tranquilo acá. Falté la
Tengo
pasada
la internet
a ver qué había.
entre cosas.
Quedan pocos sabaleros bancando el mostrador.
Sí, sí. Oh, en la última etapa de la carrera.
Sí, ¿no?
Ya me quiero sacar esta de encima. La verdad que
Esta estuvo dura, de verdad.
estuvo duro, sí.
Estuvo dura, de verdad.
Sí. Esperemos que la próxima sea más leve.
Dicen que sí.
Quiero decir, acá hay que construir el fin, ¿no? El test.
Sí, el test, pero es genérica, ¿no? Podría ser un test, un chi cuadrado, un T student. No, dice. Claro, podrían ser varias, ¿no?
Ujú.
¿Vos cuál harías?
¿Cómo, perdón?
¿Qué contestarías en la parte A?
No sé, acá lo que entiendo yo es que hay que tratar de poner un test que cumpla las condiciones estas del Q-alfa.
Q-alfa. De cuartil.
El cuantil, sí. Entonces ahí sería, no sé, a ver cómo era esto. Entonces sería, bueno, sería igual a que el asterisco sea igual al teta 0.
¿Cuál es la property 1? Aquí tenemos. Yo pondría, digo, para poner uno pondría el test statistic, ¿no? El student ese. Que calculabas la media de la normal. Que era unknown.
¿Cuál decís?
La T de students, ¿no? sea, podría ser cualquier, digamos, prueba de hipótesis.
Sí,
Está el wall test, está el... ¿Cómo te veías las cosas? Oh, qué impresionante, ¿no?
sí, no, yo voy a ver de vuelta acá. La vuelta esto.
Ah, porque todo esto va para el examen, para la prueba esta, ¿no?
Word. Sí, creo que sí.
Y yo tiraría así, un chi cuadrado o un given example, ¿viste? Porque es genérico. Y... ah, construct a test es cuando ponías el t es igual a, ¿te acordás? El phi es igual a al 1 ese de la indicatriz. Si se pone la t de student es mayor que
Sí,
q al sobre 2, ¿no? Ese es un ejemplo.
claro, claro. Claro, y ahí después lo que haces es bueno, el cuantael es el 1 menos alfa sobre 2,
Sí.
que es de q alfa sobre 2, ¿no? Sí.
Sí, porque tiene distribución para los dos lados la t.
Acá, acá
¿Cómo te
estaba
fue
viendo ahí las notas, entonces, ¿en cuál?
en el homework? ¿Cómo te fue?
En el homework, mirá, al final estuve con poco tiempo, así que nada, pude, no sé, sé que lo pasé con 70%, pero
Sí, yo igual.
a lo último fue agarrar y ya no tenía tiempo, entonces lo que hice fue agarrar las multiple choice y agarré y seleccioné las que me parecía y pegaba bastantes, entonces.
Ah.
¿A vos cómo te fue?
Sí, igual, bajé, estoy en 72, ahí lo salvé. Estamos con la materia esa de deep learning, viste que era una opcional, que era un huevo mal, me los pasé el agua y ta. Espero esta semana que estoy solo con estadística, como retomar un poco y hacer el examen.
Claro, sí, sí, sí. Sí, no, yo con esta estaba haciendo agua, imagino con otra más, imposible.
Sí.
Bueno, entonces acá te subimos. Acá tengo anotado test statistic, el t sub n es igual bueno, al de x sub n barra dividido la raíz cuadrada de S sub n dividido n. Ya no me acuerdo qué. S sub n que era.
¿Ese sub n?
Sí.
¿De dónde estás?
No, este es tenía anotado notas y estaba viendo acá
Ese sub n es la
de
varianza.
student,
Ese sub n es la varianza.
donde había notado el test statistic.
Es la varianza, ¿la verdad?
Ah, S sub n dividido n. Entonces ahí tenés, la fórmula sería me desconecté recién hace unos minutitos.
Okay. Are ready, or do you want a little more time?
No, it's okay.
Okay. Well, what about you, Nicholas? Or was it you, Nicholas? Sorry.
Sorry.
Do you want a little more time, or?
No, that's fine. Sorry, I have an internet connection that is
No. Okay, yeah, great. Okay, let's do this together. So actually the first question A is fairly simple. So you just need to define, just remember the definition. So it's just like follow the procedures that we learn. So we have like this kind of setup for this the statistical model we assume, and we want to know whether the true parameter theta star is equal to theta naught or not, theta naught or not. And so we first construct test statistics. So for this particular question, we're not asking particular test statistic, but like we say that it's gonna be called Tn, which is a function of data and true parameter, right? And we're assuming that, remember that we're assuming that this test statistics follow some distribution Q, right? And the quantile for this is Q alpha. So it's kind of 1 minus quantile. So this is what we like know from this setup. And then the test itself is going to be very, very simple actually. It's, you just say, and that's it. This is equal to, I'm just like abusing the notation a little bit here, but it's just simple. And we often denote this test as this psi in the lecture, but where psi is going to be 1 if you reject a null, and psi is equal to 0 if you fail to reject a null. So actually that's it for part A. It's very simple, but like this question deals with the core concepts of hypothesis testing. Right, so yeah, go ahead.
Where is Q alpha divided by 2?
Yes, so I'm gonna show you that we can do this without dealing with this 2 alpha over 2 actually. So this is your that's a valid question, that's totally legitimate, but we don't need to deal with that actually. And even if you're doing 2-sided test, actually we don't need to deal with 2 alpha over 2 and only Q of alpha. And I'm going to show you how we can do that without dealing with Q alpha over 2, okay? But that's a totally valid question, and thanks for asking. I'm just about to explain this with the example in the question B. So yeah, so let's do question B, which is going to be applies some example for this framework that we just covered in A. So first example is going to be Wald's test, right? And we have underlying statistical models. I'm not going to write that down, but like, or I can just copy and paste from this here. Okay. And we know that the test statistics can be written as n times theta hat minus theta naught transpose information matrix theta naught power to 1/2 and theta minus theta naught. So here I'm assuming that the parameter theta is some dimension k, which could be larger than 1, greater than 1. So that's why I'm writing this down in terms of vectors and transpose. And the information matrix is going to be information, feature information is going to be a matrix, possible, potentially. And we also know that this is going to be converge or on limit. It's going to go to chi-square distribution with the degree of freedom k. So this is like what we know about Wald statistics and the test Wald's test and test statistics. So, you know, as I just mentioned, and from the question, as we had a question from Nicholas, we know that this test statistics, if we construct the test statistics like this, we can have a very convenient form of distribution, which is a chi-square distribution with degree of freedom k. So this is like, you know, we know that, and that's a convenient, this chi-square distribution is very convenient, right? Because it's very easy to look up in the tables, and it's very simple to, so whenever you see a distribution, a quanta of the distribution you can look up on the table, those distributions are very, very easy to compute in general. So there are many other distributions that you might or might not see, and those distributions are like, you know, the distributions that you're not going to see in the future is a distribution that behaves very badly, which is very difficult to compute, for example, and very difficult to construct a quantile. But here, chi-square distribution, it's pretty easy and straightforward to compute the quantile, so we use this. So in this test, what we're going to do is that we just take the quantile, quanta alpha, because we are interested in the test with level alpha, where the Q alpha is 1 minus alpha quantile of chi-square with k degrees of freedom. So this is a frame, this is like an example where we apply the framework that we just covered in part A. So I'm gonna show you another example where we're gonna use where we're gonna like avoid using Q of alpha over 2 and instead using Q of alpha and stick to Q of alpha to construct this the test statistic. And that's gonna hopefully answer Nicholas' question. So here, let's have a little bit particular example. So we have xn, x1 to xn, which has a Bernoulli. And so the parameter space is going to be 0, 1. So we're interested in the hypothesis where H naught is equal to, say, like, or let's say this is P star. So P star is equal to P naught, and H one is not equal to P. And so the test statistic Tn. So let's do this test with asymptotic test, which uses asymptotic normality, and then we can construct test statistics like this. And we know that thanks to the central limit theorem, this is going to converge to normal distribution but with this absolute value sign staying. And we can use this distribution as a 2. Then our test size is going to be actually still Tn greater than Q of alpha, because we are like folding the normal distribution and pretend that there is no negative area, and that's why we can still use Q of alpha as the critical the quantile and critical value here. And this, we can do this because I just want to know, because we can do this because a normal distribution is symmetric. So because a normal distribution is symmetric, we can just fold it at 0. And here we can just say it's basically same as stating the absolute value. And that's, so like if you want to see graphically what's going on here. So usually if you're doing the two-sided test, what you're gonna do is like you're gonna take Q of alpha over 2 and on both sides, and this area together is going to construct quantile Q of alpha. But if we're gonna, so this is like normal with 0 and 1, but if we have a normal 0, 1 with absolute value sign, we are folding the normal distribution, so it's going to be a little bit big, right, than what we have in the on the left. And if we take Q of alpha here, this area itself, it's going to be Q of alpha. So because we're folding the normal distribution and accumulate it up on the positive side here. Does this make sense? Does this answer your question, Nicholas?
Sorry, Tomoya, the one on the right, it is a different normal distribution than the left, correct? Because it should be.
Yes, exactly. It's a little bit different normal distribution, okay. Yes. Because like that's why I'm like, I'm using the different height for this one on the left and the one on the right.
Okay.
Yeah, you're right. You're right that it's a little bit, but like, you know, because it's symmetric, normal distribution is symmetric, you can just accumulate the density at, like, for example, you can, if you take the density of -1 and 1, it's same, right? Because it's normal distribution. The density at these 2 points are same. So you can just add it up and you can still enjoy the same pretty much the same property as you can in the standard normal distribution, and with and without absolute value. So this is a little bit tricky idea, but like by creating the two distribution Q with absolute of normal distribution, we can still apply the framework we used in question A, which uses Q of alpha instead of Q of alpha over 2. Okay, so that's pretty much it for test concepts. And do you have any other questions?
No.
No? Okay, great. So then let's move on to likelihood ratio test. So this is another topic that I wished to cover in the previous weeks, but we couldn't. So this is going to be paired, like taught paired with Wald's test, I guess, in the lecture. So this test, as we learned, like that, can be used when we're trying to do test something related to MLA. So usually log likelihood ratio test, it's going to test between two models or two hypotheses, where under one hypothesis you give some constraint, and on the other side, on the other hand, you don't apply any constraint, and so like you have like basically constraint model like versus unconstrained model. So for example, if you're doing this test with like, say, let's see, always a good example. Okay, let's say, for example, you're testing whether a normal distribution has variance 1 or if that normal distribution has any free variance. So this is like typical example of constrained versus unconstrained model, where you're testing whether the variance is going to be 1 or it's going to be the other things. So you take likelihood for like this one, and you compare how, like you compare like which is more likely to happen, for example. So like that's a like kind of a constraint, and one of the constraints that you can apply. And that's a kind of like a brief overview of log likelihood ratio test. And I just want to mention one more thing, which is a little bit conceptual issue of or like illustrative issue of likelihood ratio test. So especially compared to Wald's test. So this is like log likelihood. Let's say this is true log likelihood. So what likelihood ratio test is doing is comparing like likelihood ratio at this particular point, theta naught. Let's say this one is to be theta 1, and other points theta naught. So like you're comparing the likelihood ratio between these two points. So this is likelihood ratio test. Like visually speaking, you're comparing the likelihood between particular theta naught and particular theta naught versus theta 1. And if you're doing the Wald's test, what you're actually doing is you're comparing the distance between these two thetas. So this Wald's test is doing whether, say, let's say like, maybe we should call this theta hat actually. So theta hat we get is like far enough from theta naught we assume in hypothesis. And likelihood ratio test is comparing whether the likelihood we're getting from theta naught is comparably larger, or like how large or how small compared to theta hat that we're going to get from the data. That's what we do in likelihood ratio test. So that's like a kind of visual understanding of these two tests. Maybe Philip had talked this in the class, but like I wasn't sure, so I'm just talking this here. So like these two, it's something that I really want to talk about when we before doing this exercise. But yeah, do you have any questions about this like conceptual issue of likelihood ratio test? No? Great. We all good?
Yes,
Okay.
yes.
Okay, great. Then let's go back to the exercise sheet. I'll just briefly again talk about briefly go over this question again, and I'll give you another like maybe 20 minutes to solve these questions. So, okay, sorry, let's do A together actually. I think we want to make sure this, let me see. No, let's do it. Let's do it today. I'm not gonna do this today. Let's see. Let's leave this to you as well. For the first question, we have a statistical model with parameters theta star, which has 100 dimension. So it's a 100-dimensional vector theta star, and you have observations x1 to xn, and the theta star is unknown, and the theta star, the parameter theta star, and this p is going to generate some particular random variables x1 to xn. And you're planning to use a log likelihood ratio test to check if the 25 coordinates of theta star are equal to 1. So basically, we're asking whether theta 1 star to theta 25 star. So 25 dimensions out of 100 dimensions of theta star is equal to 1 or not. That's basically what the test where we want to know. But this is like just hypothesis. So, and we're not asking you to construct any test statistics for this. But instead, we're asking what is the degrees of freedom for the chi-square distribution, which will construct the test statistics Tn and the likelihood ratio test. So what's going to happen in this particular example? What is the degrees of freedom of this chi-square? What is the degrees of freedom in this chi-square distribution in this particular scenario? That's a question. That's the question for this. Do you have any questions?
You know that the distribution is chi square, d minus r, and d is 100, is the total dimension of the parameters,
Yeah.
and r are the fixed ones. There are 25, so I think it's 75.
Yeah.
No.
So yeah. So I'll leave this to you for now. So I'm just because like we need this information in the later example. So I'll just leave this to you now, and I'm just explaining the question. So yeah. But thanks for trying. I'm not saying this is correct or this is wrong. I'm just saying we're going to get back to this later. Yeah, I'm not saying that that's wrong. I'm just saying we'll get back to this to you later. Yeah, and we have, so in the following 4 questions, we're asking you to construct test statistics for this this Gaussian distribution, and we want to test these two. We have 2 unknown parameters, but we are particularly interested in this what's going to happen to this mu star. And so we are asking you to compute the MLE, right? And we're asking you to construct basically likelihood ratio test for this question and this question. And the last question is going to be to use a stressful for this test. And you're of course you're free to use this calculator here for chi-square distribution, but like if that's too much, you can just leave this question to like and just try to explain what you need to do and what kind of values you need to look at on the table. If you were to see a chi-square distribution table. So, okay. Yeah, so let's take maybe another 20 minutes to solve this question. And of course, again, feel free to discuss. Yeah, so yeah, please try. Oh, by the way, do you have any questions before moving on? No? Okay, okay, yeah, okay, then yeah, please try these 5 questions.
Rodrigo, no, los degrees of freedom ahí, yo sabía que era 100, pero no sabía si era la diferencia con el 25 o el 25, porque ahí serían los 75 restantes son los que son libres para definir esta propiedad.
Sí, para mí son los libres, ¿no?
Sí, ¿no?
N se distribuye asintóticamente chi cuadrado 100 menos R. Y R, acá dice que R más 1 a D están fijos en la diapo anterior. O sea que de 0 a R no están fijos. O sea que es 100 menos 75, 25 me da.
25.
Sí.
Está, o sea que está. Porque no sé, aquí está fijando esos parámetros de 1 a 25.
Exacto. O sea, de los 100 te va a fijar 25.
Claro. ¿Y los degrees of freedom no serían los otros? Porque no importa. No importa lo que valga.
Yo tengo acá que la null hipótesis, o sea, como está planteada la null hipótesis, dice que deja fijo. ¿Vos tenés las diapos ahí?
No tengo.
Están en las diapos, ahí dice que de R más 1 a D son fijos. Y en este caso estamos fijando 25. O sea que R va de 0 hasta el complemento, de 100, a mi entender. Por eso 75 es R. O sea que 100 menos 75, pero es mi. El máximo likelihood estimator eso el máximo likelihood estimator es la sample mean.
Sí, ¿no? Porque aquí la distribución es gaussiana, ¿no? Sí.
Sí.
Gaussiana, sí.
¿Y la varianza, te acordás cómo era?
No era el chi, porque era el cuadrado, ¿no? Era la resta cuadrada.
La resta
al cuadrado era. Sí, era. Poco. No era la suma, es decir, la sumatoria de los x sub i menos la media, ¿no era? Al cuadrado.
Dime.
La varianza no era la sumatoria de los x sub i menos el x sub n, todo
Sí,
eso al
sí.
cuadrado.
Esa es la varianza, digamos, la definición de varianza real. Pero acá tenés que decir cuál es el estimador de la varianza.
¿Y no es ese? Porque aquí estás estimando, estás con los x sub i y tomando la media, ¿no?
Para que lo voy a googlear porque me voy. MLI Gaussian Variance. Esto era. Me da que es el estimador de la varianza MLI es. Sí, tienes razón, ¿eh?
Sí, sí.
1 sobre n por la sumatoria de x sub i menos u cuadrado.
Exacto, sí.
Sí, sí, tienes razón. Yo me había confundido. Ahí va, que estas vallas, ¿no?
Claro.
Tiene un sesgo esto.
Sí, esto. Sí, claro, si tenés un cero ahí, pero si no tenés la diferencia. Porque claro, este es el cero. Un cero. Entonces ahí estaríamos con el B, ¿no? El B estaría respuesto. Ahora sería el C, ¿no? Ahora con.
Esto lo vimos en algún lado.
Este no.
El constraint y el no constraint y todo eso. Mierda.
MLE, ¿qué es? ¿La varianza con constraint? ¿Es eso lo que significa?
¿Lo qué?
Ahí en la pregunta C, what is the MLE de qué es la varianza con constraint? El símbolo ese.
Claro, te está pidiendo que calcules el estimador de máximo likelihood, un estimadito restringido a esa hipótesis nula, ¿no? O sea,
Ajá.
te estás pidiendo que sí, que recalcules el tau.
Y no sería lo mismo, pero tomando en vez del x sub n 0,
¿Sí, no?
¿sí, no? Sería los x sub i al cuadrado.
Es la misma fórmula, en vez de u ponemos 0, ¿no? Queda y su cuadrado.
Sí, me parece que sí.
Yo creo que era eso, si no.
Y ahora en este otro, el likelihood ratio es la comparación, ¿no? De los dos likelihoods.
Sí. Ahí va, el likelihood ratio test era Tn es igual a 2 por el likelihood sin constraint menos el... Yo tengo las diapos acá impresas, ¿no? Si no, no me acuerdo ni pedo de nada. ¿Vos no tenés las diapos impresas?
No las tengo, no. ¿Vos
Yo,
las imprimiste todas?
yo al principio del curso fui a un lugar, una imprenta, imprimí todo, le dejaba crema, lo grampé ahí, lo encuaderné y chao, muy bien.
Ah, buena idea esa.
No, si no me vuelvo loco, boludo. No, no.
Sí. No, yo estoy con resumen mío, pero viste, no tengo todas las cosas.
No. Diapos a morir, con todas con unas
No,
anotaciones, digamos. No sé, cada uno
buenísimo.
estudia como quiere, es mi forma, a mí se me facilita un poco así. Tengo mala letra, también soy medio prolijo, entonces
Sí,
prefiero eso.
sí. Sí, a mí me sirve hacer el resumen porque después fijo los conceptos ahí, entonces me sirve por eso, pero me parece buena idea la que vos decís, porque siempre, a veces me pasa de que quiero ver algo en alguna de las
No,
lecturas
sí,
y a través de la aplicación es horrible. No podés.
no, te quiero morir, te vas a-
No, voy a hacer eso, si voy a imprimirlo.
Yo tengo así, mira, te mandé un WhatsApp ahí. Voy anotando, ¿viste? Porque aparte solo del cuaderno tengo. Estoy teniendo una cuadernola solo de ejercicio, digamos.
Claro,
Y de anotaciones, ¿no? Aparte de las diapos. Si no tuviese estas diapos, tendría que tener tres cuadernolas, boludo.
sí. No, está bueno lo que hiciste, sí.
Otro me está llamando. Hola.
Rodrigo,
Sí, decime.
¿no? En el último es con, ¿cómo es? El alfa 0,05 con 75 bueno, 75 o 25 de Decrease of Freedom, ¿no?
El último. Al final, para mí, era 25 grados de libertad.
Ah.
Sí.
El D yo lo planteé nomás, no
Sí,
hice
obvio,
nada.
obvio. Vamos a que lo haga y lo chequeamos.
Sí, acá, no sé, el LN, ¿qué es? ¿El logaritmo o es el
LN es el log likelihood.
log likelihood? Pero del parámetro, yo lo tengo acá escrito, no sé, capaz que lo tenés en las notas ahí.
Yo digo así, valor del log likelihood evaluado en el máximo. O sea, después que calculaste el máximo, el teta gorro, vas al likelihood y lo metés ahí y te va a dar un valor. No sé, 18,5.
Entonces tomás los dos estimadores que hallamos antes, ¿no? Los dos estimadores que hallamos
Sí.
en las partes B y C y los comparamos aplicando el likelihood. Okay.
El TNS.
Ah. Le avisamos que...
Sí, tranqui. Sí, son y media.
Tomoyo, one question. For this exam,
Go ahead.
For this exam, this mid exam, it goes all what we have studied till now, no? Or it's strengthened from the other midterm till now.
I'm not sure I'm allowed to say like exactly what's being covered, but what I can say, yeah, main focus is going to be something that you learn after the previous midterm.
But it could be any question.
Yeah, because like, because for example, like in the test statistic question, we already learned asymptotic test before the midterm, right? Before the previous midterm, but it might come again as a part of the test statistics statistics section, because we learned some new tests, but we also have something that we learned in the previous weeks. And also, like, maybe you're being asked to compute MLE as a part of the likelihood ratio test, right?
Okay.
Right, because like to compute likelihood ratio test as we're doing right now, we need to compute MLE. And so statistics in general, it's like building up. So something that you learned before, it might come again later. Okay. As a part of the new thing you learn. Yeah. So I think that's a way I think about the next midterm.
Okay, thanks.
Yeah, no worries. Yeah. I know you're most interested in that, but like, so what I'm trying to do today is trying to cover something that, we couldn't cover in the past few weeks, but is a very important topic and, can come up in the midterm or in the final as well. So yeah, I'm not saying this is going to show up in the midterm, but like, yeah, we're making sure that we're not missing anything.
Okay, thanks.
Yeah. Okay, so if you're okay, let's come back to this question. So it's the first question is about the degree of freedom. So let's first check this definition. The setup, and let's actually move back to the lecture slide, because the lecture slide actually uses slightly different notation, or slightly, I would say, maybe could be confusing for some of you. So I'll just want to recap on and kind of summarize, put it together, what's going on. So, we have a statistical like model which has a distribution P of theta star, and the theta star has 100 dimension. And we're interested in testing whether 25 of those parameters, 25 like element of this parameter vector is equal to 1 or not. So like on the other way around, this is saying that theta 25 to theta 100 can be basically anything.
Okay.
Or we're not interested in, or we're agnostic about it. And this is also the way to think about the degree of freedom in general. So especially the chi-square in like let's say in chi-square distribution case. So it's going to be maybe it's not safe to say it's in general. Let me check. Yeah, but I think it's okay to say in general. I think in general, K is equal to the number of parameters you test. I think it's okay to say that. So K is equal to the number of parameters you test. So if we were to explain this in more detail, we need to go back to the like definition of chi-square distribution, but I'm not sure we have time to do that right now. But let's just briefly explain. So chi-square distribution is that so let's say I'll stick to the definition. Then I think sorry, not definition, the example in the lecture slide, but it should be D. Yeah. So chi-square distribution D, right, is a random variable. Sorry, standard normal random variable squared, summing up to D, where each normal distribution follow standard. So this is a definition of chi-square, right? You add it up, standard normal square of standard normal distribution, and if it's degree of freedom D, you're gonna sum up D of them, right? So basically, what you think about this is like you're like assuming that each parameter so this is like an intuition, so this is not 100% correct, but how to think about this is that when you're interested in multiple parameters and each parameters, for some reason, you know that they are asymptotically normal distributed, you think you are like very close to construct a test statistic which has a chi-square distribution with degree of freedom D. And that's being applied for Wald's test or likelihood ratio test. So as we need to remember that in both cases, we need to have asymptotic normality. And asymptotic normality is like assured or it's guaranteed in MLE case. So that's why we're using likelihood ratio test or Wald's test and when we're doing MLE. But that asymptotic normality part comes in because you need to construct the test statistics, which depends on normal distribution, which is a chi-square distribution. And this kind of intuition kind of goes like, you know, it's kind of, you can back up this intuition by saying, okay, so when we want to compute the degree of freedom of chi-square distribution, it's going to be the number of parameters that you're interested in. And that number of parameters, each parameter should be normally distributed asymptotically. But so in this particular example, we have 25 parameters that we're interested in. So the degree of freedom of chi-square distribution in this question should be 25. And this was slightly different, introduced in a slightly different way in the lecture slide. So I just checked the lecture slide and it was introduced in a slightly different way, which could be a little bit maybe a cause of confusion for some of you, but I just want to make sure that, you know, lecture slide. So the null hypothesis is written in like this, right? And the test statistics from this distribution, this hypothesis is going to be d minus alpha. So in this case, we're fixing r plus 1 to d. So we're fixing d minus r parameters. So we're interested in d minus r parameters, and other r parameters are something that we're agnostic about. So agnostic about r parameters. And we're only interested in this d minus alpha parameters. And that's gonna be the parameters that we use for this. That's gonna be the degrees of freedom we use for this particular hypothesis. So basically it's the same, right? So it's just the other way around, but it's basically the number of parameters you're trying to test. And that's going to be the degrees of freedom of the chi-square distribution for the test statistic. So in this case, you're trying to test for 25 parameters. So the chi-square distribution is going to have degree of freedom 25. And the lecture slides part, Philip says, okay, we're interested in r plus 1 to d part of theta. So that's going to be d minus alpha. So the number here is d minus alpha. So that's why we're saying that, oh, sorry. By the way, theta is d-dimensional, but so that's why chi-square d minus alpha is going to be the degree of freedom of this distribution. So yeah, so that's it for part A. Do you have any questions? Or are you okay with this explanation? Okay, thanks.
Sorry,
Yeah,
so the degrees of freedom is 25.
Yes, exactly. That's 25. Yeah.
Okay.
Because we're interested in 25, we want to test 25 parameters.
Okay, thanks.
Okay. All right. So let's go to part B to DE. Okay. So part B. So we're interested in MLE and normal distribution. And I'm gonna cheat a little bit, and I'm already compute this. So I'm not gonna do the whole derivation for this, but if you have any question, I'm happy to do that. But like, so mu hat, it's going to be bar xn, and tau hat is going to be one over n times x1 minus x and summing of square summing up to 1 to n. one thing I might want to ask, is this biased or unbiased? And asymptotic.
I think it's biased.
Yeah, it's biased. Yeah, it's biased. So one thing to know, one thing you might want to remember is that the variance you get when you're computing the MLE could be biased, right? So, and this is like, yeah, this is just a brief note. If you want to have
Anyway, the
Yeah.
bias is very small because if you multiply,
yeah,
it's very small, isn't it?
yeah, so it's gonna be smaller. Yes, exactly. You're right. And biased, so this 1/n version of the variance, it's smaller than unbiased version. So which means that you might underestimate the variance, right? So just a little bit practical. This, what I'm gonna talk about now, is a little bit practical thing. But the reason why some people prefer unbiased version over biased version, when the biased version is more easy to compute or easy to derive, is that unbiased version could be more conservative. So when you say the variance is conservative, it's going to be like larger. And this, conservative version is sometimes important because you want to be very confident about your result or your conclusion you're going to draw from the statistical test or whatever, whatever, like maybe confidence interval, whatever. If you have a smaller variance, right, you might underestimate the variation you're getting from the estimate, which means that you are overconfident about your about the conclusion you draw. And that's why you sometimes prefer unbiased estimate, which is more conservative, we had a larger variance in general. Does this make sense? Like, yeah, this is what I'm just talking right now is totally like, it's not super relevant for the midterm maybe, but like I think it's very, very important in practice. Anyway, yeah.
Okay.
Yeah, let's go back to the questions. Yeah, so C is okay. So next, compute the constraint MLE as specified. So it's going to be H naught. It's going to be based on H naught mu star equals 0. So let's do this a little bit to little bit of derivation for this, because this is going to be a little bit tricky. So we are fixing the mean of the normal distribution. So basically under the null, x1 to xn is distributed IID from normal with 0 and t star. All right. And just for comparison, under H1, so maybe we should be consistent. So let's say under the null, sorry, I ran out of space, but under H naught, under H1, x1 to xn follows this normal distribution. So, or something other than 0, mu star something other than 0. And that's our hypothesis. So we're saying that this H naught is constrained because we fix mu star equals 0. So this fixed value mu star is our constraint. And under the alternative hypothesis, we're not fixing the value of mu. We are, unless it's 0, we allow mu star to take any value. That's going to be like unconstrained. So in the likelihood ratio test, it's going to be the test between constrained null hypothesis versus unconstrained alternative hypothesis. So based on this, under the null situation, we construct a likelihood. And that likelihood is going to be x tau and mu equals 0. So the normal distribution has, so this normal distribution is going to be centered. So we don't have the minus mu term because we are allowed, we say minus mu is equal to 0. And we can construct, so this is like for one observation. So for entire n observation, what we need to do, can someone remind me what we need to do?
The product.
Yeah, product of all of n, because it's IID. Yeah. So we just simply take product of n observations. And yeah. So that's our likelihood. So we can take log likelihood of this and take the first condition as we usually do. That's maybe, so we are a little bit running out of time, so I'm just going a little bit quick here. And I have a cheat sheet, not my cheat note, so I'm just follow the cheat note. And it says, no, it's going to be minus. It should be minus, of course. And you take the first derivative, you take the first condition with respect to t. Not t, sorry, tau. And then you get tau for, let's say, constraint model, if you could see for constraint. And it's going to be n over 1 times x1 squared 1 2 n. Right. And this contrasts with this let's say this is tau hat u, which is unconstrained model. And so you, in sum, for the unconstrained, it's gonna be mu hat unconstrained is equal to bar xn and n over 1 and this usual biased version of variance formula.
What is the meaning of FOC?
Sorry?
What is the meaning of
Oh, sorry. Yeah, sorry. This is first order condition. Sorry, I should have mentioned. Thanks. Yeah. No. Same to you. I was abusing the notation. Sorry. And for constraint model, of course, we know that mu is equal to 0 because that's our assumption. And if so, the variance is going to be this. Okay. Do you have any question so far about this construction or like likelihood we get? Oh, the estimate we get?
Nope.
No? Okay. All right. Okay. Then let's go to question D. To construct a likelihood ratio test. I'm not going to ask you, maybe. Yeah, so we are just asking to construct a likelihood ratio test. So it's just simply go back to the formula, right? So it's going to be log of L likelihood ratio with mu hat and tau hat and constraint minus the constraint version. So it's going to be x1, xn, mu hat equals 0, and tau constraint. And close the parentheses. So this and this is going to be converged to. Do you have any idea what's the degrees of freedom for this question? So it's going to be 1 because our hypothesis is about mu, right? So our parameters we're interested in is only 1. So this is 1 because we are only interested in mu, which has dimension 1. So, in general, in the likelihood ratio test, how you construct it is that you're gonna take the difference between the likelihood ratio between, let's write it down in the words, log likelihood for unconstrained minus log likelihood for constrained. And this is going to be converged to chi-square of the k, where k is number of dimension, number of parameters or dimension, number of parameters or dimensions you test. Okay, so that's pretty much it for question D. And for question E, I will leave this behind because it's just like you just go look up the chi-square table and look at the it's gonna be no, it's okay. It's level Q alpha, and you just go and look up the table for degree of freedom 1 case. So I'm not going to go into detail for this, but yeah, you can do that by looking into the table that we've just posted on. We just put it on the top of the lectures note. So, do you have any questions?
No, it's okay.
Okay, so then we're pretty much running out of time. So I just want to do 3 questions on the top of this Jeffreys prior question and together, and I'm going to close this session today. It should be fairly simple. So we're asking some conceptual issue of Jeffreys prior. So the first one is asking whether Jeffreys prior is improper or not in some cases. Is it true or false?
I think true.
Yes, it's true. Yeah, it's true. So in some cases, especially, this particular example in question B here, actually, so this, I'll just give you the answer to this, but this should be T over 1 over T. And this T is going to be 0 to infinity, which means that this is this is an improper uniform distribution. So the Jeffreys prior could be improper, yes. So question 2, the specific form of Jeffreys prior depends only on the underlying statistical model. Is it true or false? the hint is here. Does the data comes in the Fisher information?
No.
Yeah, no, right? So the data doesn't come in, no data here, which means that
It's true that
yeah, it's true. Yes, exactly. So the Jeffrey spread doesn't depend on the data, but it does depend on the statistical model you assume, which is supposed to construct the data you observe. So you're not going to compute, you're not going to construct Jeffrey's prior from the data, but that's going to come from the likelihood or the statistical model you're going to assume. So that's kind of a difference, slight difference, but like that's also pretty important. And the last one is a little bit tricky, and I need to run around my head as well. But like, if the asymptotic standard deviation of the MLE for theta is relatively large, then Jeffrey's prior is relatively small at theta. What do you think about this?
you got to check the Jeffrey's prior is the square root of the feature information, and the feature information is the inverse of the variance.
So this is, sorry, true or false? So
True.
right, you're right. So feature information is the square root. Sorry, the Jeffrey's prior is the square root of feature information, and if it's one dimension, right? The feature information, 1/feature information is going to be the variance of the MLE, right? Which means if the standard deviation is small, feature information will be, sorry, yeah, so sorry, it's all the way around. Standard deviation is large, feature information is, sorry, small, which means Jeffrey's prior is also
small.
Yeah, so this is also true. Yeah, thanks for participating. Do you have any questions, by the way, for these questions?
No, it's okay, Tomoya, thank you.
Yeah,
Thank
okay. Yeah, so that's it for today. I'll be around as well for a little bit, but you can feel free to go. I'm gonna stop recording.